Hello. In this lecture, we'll first learn about Cayley graph of a finitely generated group, and then we'll learn about quasi-isometries. So corresponding to a finitely generated group, you can have this Cayley graph, and suppose you change the generating set, so then you'll get two Cayley graphs, and these Cayley graphs will be quasi-isometric to each other. So let us first begin with the definition of the Cayley graph. So let us start with a finitely generated group. So let G be a finitely generated group with finite generating set S. So G is generated by this finite set S. So we'll define a graph gamma GS as follows. So this graph will be called to be the Cayley graph. So the vertex set of this graph is the whole group G. So in order to define a graph, so we should have vertex set and S set. The vertex set V comma GS is the whole group G. Now I have to define the S set. So let us take two elements of this vertex. So let G prime belongs to this vertex set. So the vertices G and G prime have an edge between them if G inverse G prime belongs to S, or the inverse of this G inverse G prime, so which is nothing but G inverse G prime inverse G, so this belongs to S. And in additional, so you also demand this thing. So in additional, if for some A belonging to S, A square is equal to the entity element. So 1 is the entity element. Then between 1 and A, there are two edges labeled by A and A inverse. So suppose this A square is equal to 1. So then we also demand this thing. So A will be equal to here A inverse. So between 1 and A, we have an edge, which is labeled by A. And from A to 1, again, you have this edge. You can give a direction. So this is A inverse. Okay, so now let me come to examples. So let us first start with this free group of rank 2. So G is this free group of rank 2. The generating set is AB. And now I want to draw this Kelly graph. So first, let us start with this entity element 1, and let us take the generator A. So 1 inverse A, it belongs to the set S. So therefore, there exists an H between this 1 and A. Now let us take A and A square. A inverse A square, or A square inverse of A. Yeah, so sorry. So if I just take A inverse A square, so that is equal to A, so it belongs to S. So there will be an H between A and A square. And note that if I take 1 and A square, these two vertices, 1 and A square, 1 inverse A square, so that is equal to A square. So that does not belongs to S. So you will not get any H between 1 and A square. Now let us take A inverse. So between A inverse and 1, so there will be an edge. And you can continue this process. Between A square and A cube, there will be an edge. So you'll get a line corresponding to the cyclic subgroup generated by A. Now let us take the generator B. So 1 to B, so again you will get an edge. B to B square, you'll get an edge. And in the other direction, between 1 and B inverse, there will be an edge. B inverse and B minus 2, so there will be an edge, and you can continue this process. Okay. So now let us take the word AB. So let us take the word AB, and let us take the other generator A. So A inverse AB, so this is equal to B. It belongs to S. So therefore, A and AB, there will be an edge. So let me draw in this way. So between A and AB, there is an edge. You can label this edge by the letter B. And now if I take the these two elements, A and A inverse B, not A inverse B, AB inverse. So again, if I take AB inverse and take the inverse of this AB inverse, so AB inverse, this thing is equal to B, this belongs to S. So there will be an H between this A and AB inverse. So this H, you can label it by B inverse. So here also you'll get an edge. So this vertex will be AB square. Similarly, in this direction also, you'll get this edge, and you can continue this process. Okay. Now let us take the word BA. And if I take these two elements, A and BA, so A inverse BA, it does not belongs to S. And if I take BA inverse A, so this is equal to your A inverse B inverse A. It also does not belongs to S. So there does not exist any H between A and BA. But if I take this two words, B and BA, so B inverse BA, so this is equal to A, it belongs to S. So there will exist an H between B and BA. So here it is justified that this group G, which is a free group on these two elements, A, B. So this is a non-commutative group and you do not have any relation. So BA is not equal to AB. Now, similarly here, in the other direction, so we'll get BA inverse. We'll get an edge between BA square, and note that, so this blue horizontal line, it will not intersect with this red line. Okay. So now corresponding to each of these vertex, so either you will get this vertical line or you will get this horizontal line. So for each vertex, yeah, so you'll get this two kinds of lines. One is the vertical line and one is this horizontal line. So these lines, they will intersect only at a single point. Okay, so what is this Kelly graph? So this Kelly graph, gamma GS. So this is a tree. Such that the degree of each vertex is equal to 4. So this, in fact, it is an infinite tree, infinite regular tree, such that the degree of each vertex is equal to 4. Now let us take another example. So let us take this group G to be Z cross Z. And this group can be represented as follows. It is generated by two elements A and B, and you have this relation AB A inverse B inverse equal to 1. So this is a presentation of this group Z cross Z, and corresponding to the cyclic group generated by this A. So again, you will get this horizontal line you can take. And corresponding to the generator B, you can take this vertical line. Again, between this AB and A, so there will be an edge. So in fact, from this A, you'll get a vertical line. And you'll get this point here, this vertex here. This is my AB. And then you have this AB square. And now this AB, so this is equal to your BA. So in Z cross Z, AB is equal to BA. So now between this B and BA, you'll have an edge. So you will have an edge between this B and BA. So in fact, you'll get this horizontal line here. So in fact, the Kelly graph, so this will be this lattice in R2. Yeah, so you'll get this lattice in R2. So this is the Kelly graph of this group. Okay. So the third thing, so I'll give this as an exercise. So consider this group generated by A and B. So where the relation is A square is equal to B cube. So one can prove that this is isometric to Z. So G is isometric to Z. And for this Z, the Kelly graph of Z, it is just a horizontal line. And but for this group, the Kelly graph will be different. But so there is something called quasi-isometry. So one can prove that the Kelly graphs are quasi-isometric to each other. Okay. So now we are in a position to define quasi-isometry. So let us do that thing. Okay, start with two metric spaces x1 and x2 with metrics d1 and d2 respectively. And let us take two numbers, so k greater than equals to 1 and epsilon greater than equals to 0. A map phi from x1 to x2 is said to be k epsilon quasi-isometric embedding. So if this inequality is satisfied, so 1 by k times distance of xy in x1 minus epsilon is less than equals to distance of phi x, phi y in x2, that is less than equals to k times the distance of xy in x1 plus epsilon. So here you note that if I take epsilon to be equal to 0 and k to be equal to 1, so then phi is just an isometric embedding. So this quasi-isometric embedding, it is a generalization of the isometric embedding. A map phi from x1 to x2 is said to be k epsilon quasi-isometry if this map phi is k epsilon quasi-isometric embedding, and in additional, it is k coarsely surjective. So that is, if I take any element y from this codomain space x2, so there exists a point x in the domain space x1 such that the distance between phi x and y is less than equals to k. So if k, suppose k is equal to 0, so this means that this map phi is surjective. But here I have taken this k to be greater than equals to 1. So this means that phi is coarsely surjective. And this map phi is called quasi-isometry if there exists some number k greater than equals to 1 and epsilon greater than equals to 0, such that this map phi is k epsilon quasi-isometry. Okay, so example. So now let us take the Kelly graph of the Z cross Z, where the generating set is 0, 1 and 0, 1 and 1, 0. So you can take it to be generated by A and B, where the relation is A B inverse B inverse equals to 1. So the Kelly graph, so this will be this lattice in this R2, the square lattice in R2. And now what is the metric on this graph? The metric on this graph is as follows. So let us take two points, P1, Q1 and P2, Q2 in this graph gamma. So the distance in gamma is equal to the mod of P1, P2 plus the mod of Q1 minus Q2. For instance, if I take these 2 points, so let us take these 2 points. So the distance in this metric, so first you go from here to here. So take this path. So this horizontal length plus if you take this vertical path and take the length of this vertical path, so this vertical length, and if you add these two things, so you'll get the distance between these 2 points. So that is the metric on this gamma, and gamma it naturally embeds in R2. And what is the metric on R2? It is the Euclidean metric. So this Euclidean metric. So one can prove that, so distance in R2 is less than equals to distance in gamma, and that is less than equals to twice of distance in R2. And also if I take any point xy belongs to this R2, so there exists a point on gamma such that the distance of xy to that point is less than equals to half. So this is clear from this picture. So distance of xy to gamma is less than equals to half. So therefore, this embedding of this gamma in R2, it is a quasi-isometric. Okay. So now the thing I was telling, so let G be a finitely generated group with two finite generating sets S1 and S2. So G is generated by S1 and G is generated by S2. Both S1 and S2 are finite. So then we have an identity map from this the group generated by S1 to group generated by S2, and that this identity map, it is in fact it is a quasi-isometry. So this identity map, in fact, it will induce a quasi-isometry on the Cayley graphs. Okay. So now let us take this S1 to be this set A1, A2, AN, and S2 to be this set B1, B2, BM. And let GI be the group generated by SI, I equals to 1 to 2. So note that this G1 and G2, so it is they are both equal to G. So now let us take G belongs to G1. So then, so this G, so this is equal to A1 to the power I1 dot AN to the power IN. So this group G1, it is generated by this A1, A2, AN. So any element of this G1, it can be expressed as the product of this A1, ANs. So that is the thing I have written it here. Okay, so now also observe that, so this AI, it also belongs to G2. So G1 and G2 both are same. So here G2 is generated by the elements B1, Bm. So this AI, it belongs to the group G2. So therefore, so this AI, it will be a word in this B1, Bm. Okay. So now let us take the length of this word Wi in G2. So here length means the following. So if I take some word, let us take W to be B1, J1, BM, JM. So length of this W, it means that summation of all this mod of this J R. For example, if I take this word B1, B2, B1 inverse, B1. So this word, it may not be reduced, but the length of this word is 1 plus 1 plus 1 plus 1. So this is equal to 4. So length of this word is 4. Okay, so now what I do, so I take this K1 to be the maximum of length of the word Wi in G2. So length of this Wi in G2, it means that is the number of bj's appearing in Wi. Okay. So now, so this G, so this is again, it is something like this. A1 to the power I1 dot dot an to the power in. Length of this G in G1, so this is equal to summation j equal to 1 to n mod of this ij. And each of this ai is equal to wi. So we have this equality here. And now length of this word g in G2, so which is equal to summation j equals to 1 to n length of wj times mod of this ij. And length of this wj, it will be less than equals to k1, because k1 I have taken it to be the maximum of the length of the words wi in G2. So the length of this g in G2, so this is less than equals to k1 times summation j1 equals to n mod of ij. And this is nothing but the length of the word g in G1. So what we have here, length of g in G2 is less than equals to k1 times length of G1, length of g in G1. So similarly, so there exists k2 such that the length of g in G1 is less than equals to k2 times length of g in G2. And let us take this k to be maximum of this k1, k2. So then 1 by k times length of g in G1 is less than equals to length of g in G2 less than equals to k times the length of g in G1. Okay. So now let us take two elements g and g prime in G. So what is the distance between this g and g prime in the group gi, where I is equal to 1? So how do you define the distance between g and g prime? It is the infimum of the length of all words w. So this word w, it represents the element g inverse g prime. So for this g inverse g prime, so there can be several words which represents this g inverse g prime. So you just take the infimum of the length of all those words which represents g inverse g prime. Now from this this equation, so now from this equation, so what we'll get? So from this equation, so you'll get 1 by k times distance between g and g prime in G1 is less than equals to distance between g and g prime in G2 less than equals to the distance between g prime in K1 times k. So this will prove that with respect to this metric, the groups G1 and G2 are quasi-isometric to each other. Also note that so this metric is called word metric. So this metric is called word metric. So with respect to what metric, so these groups G1 and G2 are quasi-isometric to each other. So therefore we have proved this theorem. So if I take a finitely generated group with two different finite generating sets S1 and S2, so then with respect to the word metric, the group generated by S1 will be quasi-isometric to the group generated by S2. Now if I take the Cayley graph, the vertex set of the Cayley graph is G itself. And now if I take the Watt metric, the distance between the vertices in the Kelly graph will be same as the Watt metric. So with respect to Watt metric, these two groups are quasi-isometric to each other. And so this vertex set is nicely embedded in the Kelly graph. In fact, it is quasi-isometrically embedded in the Kelly graph. So therefore, so the Kelly graphs will be also quasi-isometric to each other. So that is very easy to check. So I'll leave this as an exercise. Okay, so I'll stop here. And in the next class, so I'll prove that. So this Swark-Milner lemma, so it states that if a group, if it acts properly and co-compactly on a geodesic metric space X, and also assume that that group to be finitely generated, so then the Kelly graph of that group will be quasi-isometric to the geodesic metric space X. Okay, so I'll stop here.